Thank you so much for joining us. We have a guest speaker session today with Kaushik Valmeekam. Kaushik is a doctoral candidate in electrical engineering at Texas A&M University, working under the guidance of Professor Krishna Narayanan. His research interests are at the intersection of machine learning and wireless communication, and research works are based on a variety of topics, including text compression using large language models. And this talk today is on the paper LLMs lossless text compression using large language model. Thank you so much for joining us today, and thank you for your time. Kaushik, over to you.
Yeah, yeah. Thank you so much, Ahmed, for the introduction. Are you able to see the screen?
Yes, we can see the screen.
Yeah, perfect. Hi, everyone. I'm Kaushik Valmeekam. I'm a PhD student in A&M, and I work with Professor Krishna Narayanan. And this is our joint work with Professor Krishna Narayanan, Professor Chamberlain, Professor Dilip, and Professor Srinivas. And this is about lossless text compression using large language models. So the talk has the following outline. We are going to introduce a bit the main theme of this problem, explain what lossless compression is, go through what we are doing in LLM Zip, go through some of the results and some other recent works that have popped up. Uh, yeah, so let's begin. So the main theme of this work is it's well known in the community that learning, prediction, and compression are very interlinked. And it's also known that language models are exceptional at predicting the next token given a set of tokens in the context. And LLMs have been seen as being in the intersection of learning and prediction. And we want to change the view in bringing LLMs in the intersection of learning, prediction, and compression. Because the main idea here is that good prediction implies good compression, and this is not an idea that we have come up with. It has been well known in the compression community for a very long time, but we would like to bring this to the limelight, especially for the LLM community as well. Uh, so let's look into the problem of lossless compression, lossless compression of English text. In this, we are given an English text with some NC characters, and the aim of the encoder is to convert these text into a sequence of bits of some length NB, and the decoder then has to convert this bit sequence back to an English text, which is some S hat. And in lossless compression, we want S hat to be equal to S. So we want the text to be the same. And the compression ratio here is defined in bits per character, so NB or NC. And typically, the state of the art compression algorithms like Zip especially is based on Limpelzev and Huffman coding. These are some of the popular coding compression algorithms. And recently, there has been a lot of work in more tailored algorithms and even like PAQ, series of algorithms called PAQ. So they are very tailored to text as well, and other images as well, and even neural network based stuff have been existed, like LSTM based, even transformer based compression techniques have been existed. And there are also well-known competitions and benchmarks for text compression. But in this work, we were interested in what is the fundamental limit of compressing English text. How low can we actually go if we're given a lot of power? So to get a sense of how prediction and compression go well hand in hand, we can look at the Shannon's prediction game. And so I would urge you all to interact if you can. So let's take a look at this two words we have, FR, and we let's try to complete this word. So what would be like a first guess for what the next word is given F and R, the alphabet?
E.
Yeah, E is one guess. And what can be the other guess? Maybe I for friend. So if you think about friend, it's I. If you think about French, it's E. If you think about France, it's A. So these are like three possibilities. So let's say if it's just me and your, I want to, in the end, I want to be able to compress this and decode. So my guess, first guess is I, second guess is E, and third guess is A. So then what I can do is, if the actual word was, let's say, friend, so then what I can do is the word, instead of trying to save the word I can just try to look at the rank of the word of the true letter I in my guess, and then compress just the rank. So in my guess, the rank I is 1. So, and I have like 5 guesses. So I would need at the most 3 bits to compress I. Whereas if I were to compress the letter, it's 26 alphabets, and I would need somewhere around 6 bits, I guess. Uh, so the idea here is that with these sort of guesses, you can compute the conditional probabilities of the next word or the next alphabet, and then uh, based on these ranks you can come up with an entropy rate estimate. And that's what Shannon had done. He used human beings to predict the next words and give some guesses, and based on that they computed that the entropy rate of English should lie somewhere between 1.4 bits per character and zero point 0.6 bits per character, and this was done in 1951. uh, and then Cover and King, these people have sharpened this bound to 1.2 bits per character, the upper bound. And more recently, people have also tried using neural networks to then come up with this prediction. So this is exactly what we are doing in LLM Zip as well. We use the LLM to make the guess for us, to give us the conditional probabilities. And then we use the conditional probability to compress the text. Yeah, so here's how our LLM Zip encoding process works. So you have your text and it goes through a tokenizer, so you get a sequence of tokens. By the way, feel free to budge in if you have any questions. Yeah, so you have a sequence of tokens, and now you want to compress these sequence of tokens. Uh, so the LLM gives you the conditional probability of the next token, conditioned on the previous on a context which is of size m. So previous m tokens it takes in to predict what the next token could be. So it gives us a conditional probability. What we use is, since we already know what the current token or the ith token is, we use the conditional probability estimate from the LLM and the current token to then compress this using arithmetic code. And the way an arithmetic encoder works is, so uh, if you give it a conditional PMF, the arithmetic encoder tries to divide the number line between 0 and 1 into intervals based on the conditional probabilities you have provided. So let's try to get a sense of this by looking at how the encoding works. So let's say in the LLM case, we always start with the start token to get the prediction on the first token. So once we start with the start token, we have a conditional probability on the first token, and the arithmetic encoder divides the number line between 0 and 1, and we figure out that the first token is x1 and it lies in this interval. So then we want to compress the next token, and so the next token is passed to the LLM along with the first token x1 is passed to the LLM, and then we get an estimate, the PMF for the second token. And we see that the second token corresponds to some other interval here. And the important thing is the arithmetic coder further divides this small interval based on the new PMF. Uh, and if we continue this process for the next set of tokens, in the end, we will have one floating point number, let's say 0.1. So this is in binary. So you'll have one floating point number. But the important thing is this floating point number lies in all the intervals uh, corresponding to the token. So you have one floating point number essentially representing the sequence of tokens that we are trying to compress. And this is actually very, uh, this is the best you can do if your conditional PMF is optimal. Uh, uh, so, but in our LLM, it's approximating the true conditional PMF. So there is still some slack there. And this is exactly how the arithmetic encoding works. So now you might wonder, how do we decode? So in the decoding process, we again always start with the start token to get the PMF of the first token. And now we have just the input, which is our floating point number. And given the intervals, we know that this floating point number will lie in a corresponding interval. And based on the interval, you can get back your token. You pass the next token into the LLM, get the PMF of the next uh, X2, and then you see where it lies, where the floating point number lies, and you can get X2 as well. So this way, you can decode back the entire sequence of tokens. And yeah, this is how LLM zip works. We use arithmetic coder and LLMs in this fashion. So this is actually a well-known idea using a predictive model and an arithmetic coder. But what is surprising was the results, where we've seen that like Llama 2 in our case has a compression ratio of 0.7 bits per character, whereas the state of the art then were having around 1.4 bits per character. So that is huge. So each character, which is of 8 bits, have been compressed to just 0.7 bits when you use Llama 2. And this is actually closer to the lower bounds predicted by Shannon. And that's what was interesting, is because most of the state of the art results were nowhere near even the upper bound, actually. Uh, so this clearly shows that LLMs are doing extremely well, especially with English text, in predicting and in compression. Um, and interestingly, we've also tried to see how it varies. So we have a context size. So if you have 31 tokens in the context, and then you're predicting the 32nd token, uh, the performance is at 0.9, roughly 0.9 bits per character, but it's still better than all the state of the art. So even just with 32 tokens, it's able to predict reasonably well. And as your tokens context size increases, you obviously get better and better performance. But yeah, uh, so this clearly shows us in some ways what LLMs can enable if they can be run fast, uh, uh, and optimized for their inference is optimized. And that's what's exciting for us. It kind of, we do believe that this is going to be the future of compression, and it sort of shows us a glimpse. Although we had to run it on GPUs and all to get these results. Uh, but more interestingly, it is that the language modeling problem, the way it was designed, is in fact designed for compression. Many of you might be knowing it, but essentially the LLM is trained for maximizing the likelihood of X. And here, so if you look at the cross entropy function, so the cross entropy of the true token would just be the log of qi of xi, where xi is the correct token. And so if qi here denotes the conditional probability conditioned on the context of tokens. And if p were to be the true conditional probability, then we can rewrite the cross entropy loss in the following way. uh, where you divide and multiply by the true probability, and this actually with as n increases, this should converge to the entropy rate of the process X, or the language process in this case, provided it is stationary and all. But it kind of gives us a sense of what is the loss function that we are using. And indeed, this quantity actually represents the number of bits needed to compress X, uh, given the assumption that X is generated with the distribution Q, whereas in reality, X is actually generated from the true distribution P. So then this is really the number of bits required, and we are indeed trying to minimize that quantity, which is reduce the number of bits required. So in that way, language modeling is naturally optimized for compression. And not only that, we also run some preliminary results with looking at using compression with summaries as side information. So the idea here is, so consider a text that we are trying to compress, and so g of s here denotes the summary of the text. It's some function of the text itself. And if you consider a two-step compression where you first compress the text, and then first you compress the summary, and then you compress the text conditioned on the summary. So technically the entropy would be the same. So the joint entropy of the text and the summary would be equal to the sum of uh, the entropy of text and the conditional uh, entropy itself. So if we had an optimal compressor, then compressing the text itself, or compressing the summary and then compressing the text, they both should be equal, and they both will be equal to the true entropy of the text itself, if you had an optimal compressor. But uh, uh, we also look at the case where we have the summary at both the encoder and the decoder. In that case, you would need fewer bits, or the entropy, the conditional entropy would be smaller than the true entropy. So you can get away with fewer bits for compression if you had summary at both the ends. But with a suboptimal compressor, this need not be the case. That is, you might actually do better if you try to compress the summary and then compress the text condition on the summary, because the compressor is not necessarily optimal. Uh, so there is a possibility that you might be doing better, and we wanted to investigate this. Uh, and definitely, if you have the summary at both the ends, you should do better. Uh, uh, so that is the idea. And the results that we have observed, this was just on a paper in archive. We just took a paper from archive and we tried to compress it. We generated a couple of summaries of varying lengths, and using GPT-4. And also we have considered looking at the abstract as a summary, and just the first paragraph as a summary. So and then what we observed was that indeed using some form of summary or some form of information, additional information, you do better than when you have the encoder and decoder at both the ends. You do better than not having the summary, and that is consistent with what we expected. uh, and interestingly, even if you were to transmit, so in the case of, if the summary was only at the encoder, you need to compress the summary and also transmit, you need to take into account the bits of the compressed summary as well in computing the compression ratio. So in that case, what happens is that there are some optimal summaries where you do extremely well. So in this case, the summary with 428 tokens is doing the best in terms of compression ratio, whereas even a longer length summary should indeed do better, but we don't see that. Like 945 and 473, these tokens are larger in size, but they don't necessarily encapsulate the text well enough that it actually improves the combined compression ratio. But in all these cases, it is still better than having no summary uh, in the context. Uh, yeah, and this is really the idea. And if you were to just use a paragraph, which is not necessarily a summary, it does worse than all these summary and even the abstract, which is in some ways a summary of the paper. So this is a very preliminary result on how summaries which are available in some use cases can be used to compress better and offer a varied range of compression as well. Uh, yeah, and yeah, now I would like to sort of look at some other works which I thought were interesting and also give a more insight on what people are trying to do with compression and transformers and stuff. So the first paper is language modeling is compression. This is a work by DeepMind, and this work was extremely interesting for us because not only did they show that they indeed do better compression, obviously, but if you take into account the size of the model, they are not comparable to gzip or others. Other compression techniques, but indeed they were consistent with our results as well, that they do offer very good compression rate, raw compression rates. And but what was interesting is that the transformers that they trained, not when they trained it for text, they not only offered good compression on text, but they also were able to do very good compression on images and speech as well, even though they were not trained on that. And that is very surprising. And these patterns were observed in the large language models, and but the smaller transformers didn't do that well. Uh, and what this indicates to us is it is mainly due to it can be attributed to the in context learning abilities of the LLMs, because this shows us that indeed, even though the LLMs were trained for text, even when you give it data that is actually from images, it is able to adapt to the patterns that are available in context and sort of neglect uh, uh, the inherent language understanding it has, and then do the best it can in some ways. So that is what it indicates to us, and that is like extremely exciting to see these results. And they have also had an interesting part about how tokenization and compression are related, and I thought it's worth sharing for this audience as well. And so what they say is that transformers are known to be bad for very long context lengths. So the reason we have tokenizers is so that we can sort of compress some of these texts to some extent and have shorter sequences. So if your tokenizer has smaller vocabulary size, you tend to have longer sequences. And when you have longer sequences, your context, because it's limited, you'll have less information in the context for the transformer to use. Whereas if you take the case where you have a larger tokenizer vocabulary, you have shorter sequences, more information in context, but the classification problem. So now you have to, in the case of Llama, it's 32,000 tokens. So now you have a harder classification problem. And you have to classify from 1 out of 32,000 in very large tokenizer vocabulary sizes. But theoretically speaking, what they say, and it makes sense, is that in the case of small vocabulary sizes, you have an easy prediction task, and you also have less information in the context. Whereas in the case of larger tokenizer vocabulary, you have a harder prediction task and also more information in context. So theoretically, these effects should cancel out and they shouldn't really impact. But empirically, what they observed is that the large language models were able to work better with smaller vocabulary sizes. This is their empirical result. And smaller language models were able to work with large vocabulary sizes. And one way I sort of made sense with this result is that in some ways, larger language models are better at handling longer context lengths. And the difference between the LLMs with smaller vocabulary sizes and the LLM with larger vocabulary sizes is that per information bit, they're able to have more processing power. Whereas the smaller language models, per information bit, they don't have. I mean, if you have a smaller or a larger vocabulary size, your per information bit uh, uh, processing power reduces. So that way, since they handle long context well, I think that's why empirically they might be seeing that LLMs and small vocabulary sizes seem to work well. But this is again one empirical result, and it's still interesting as a result. So that I thought it might be worth to share. And not only that, people have used this transformer plus arithmetic coding even before us. In this work by Meta, where they have the speech compression and they extract features using a convolutional networks, and they use a transformer to predict a sequence of indices from the vector quantizer. So uh, they use it in a similar fashion that we did, where they have a prediction network and they have the arithmetic coder. And what they see is the results are when they use the entropy coding, which is transformer plus arithmetic coding. They see that there is an increase, a significant improvement in the compression performance. Uh, but overall, this is the sense that the main message here is again, good prediction implies good compression, and language modeling especially is indeed designed to compress text, and LLMs do offer state of the art text compression. Yeah, thank you. If you have any questions, please let me know.
Thank you for the talk.
Yeah.
So I have a question that what is the encoder model that you are using? Because generally LLMs are like decoder only. So are you using a separate encoder model?
No, so the LLM is the encoder itself. It's the same LLM at the encoder and the decoder. So the LLM, essentially you can get the conditional probabilities. So if you give the set of tokens, the LLM gives you the probability distribution on all the tokens, right? And what we are doing is we are using this with an arithmetic encoder to encode, and we are using the probabilities again with an arithmetic decoder to decode. So the LLM acts as the probability model, and the arithmetic encoder is actually doing the encoding here. But the power of, or the performance comes because of the prediction capabilities of the LLMs.
Right, right.
Yeah.
Yeah, I have one question for you, Chandra.
Mhm.
What if the case is a bit different? Let's say
Mhm.
you're quantizing or chunking down uh, the sign language into text and then zipping it together. What could be the difference here?
Uh, Sorry, could you repeat? Or could you repeat what do you mean by that? So you want to like?
Look, I already have a framework set up for
Okay,
converging of sign language into text, right?
okay,
I just
yeah.
want to zip the file so that
Mhm.
it doesn't, lose the whole data that I have. But I also want a good processing power at the same time. So can this concept be implemented in that way as well?
Yeah. So if you want to compress the text, indeed you can use this framework to get extremely good compression. But the thing is, this as a concept makes sense, but in practice, you need to run the LLM on a GPU for compressing your text, whereas the gzip model, or whatever zip compression you have inbuilt in your computer, can run in seconds. So currently, yeah, it's not there yet for you to use it off the shelf.
Got it. Thank you.
Right. Yeah. Yeah, actually, so the one way I think of what is happening here in a very naive or intuitive way for me is that, so when you're trying to compress some text, uh, and if you have an access to an LLM, you don't have to store the entire text. You only have to store the stuff that the LLM doesn't know in the text. In some ways, that is what is happening here. You're sort of capturing the uncertainty of the text in the LLM, about the text in the LLM, and just storing those aspects. And so that if you have the same LLM at the decoder, you just need those uncertain parts to correct it when it is wrong in the prediction, and that way you're able to get away because the LLM already knows a lot of stuff already. You don't need a lot of bits to store. That's the reason why we see this performance.
There is a question in chat.
Yeah, sure. Yeah, I think yes, diffusion. It is something we have been considering as well, using diffusion to compress images, but it becomes a bit uh, harder in the sense that in diffusion you're trying to sort of predict the noise. uh, it should be able to done because it does capture the noise model uh, pretty well. So in theory, yes, especially if you have a transformer based diffusion model, it should be done, but the details of it have to be uh, charted out, and it's definitely an interesting idea to explore. But yeah, this opens up for people to look into uh, the generative models and see how they can be used for compression as well. Yes, yeah, something along those lines. Store a noisy image and let diffusion fix it. Yes. Yeah. The the idea is that because we have such powerful generative models, and it might become and as these models get uh, more accessible to run on smaller devices, it might make sense for us to store, like, essentially let them produce most of the time and store only stuff that we need to correct in them. And this gives rise to very interesting ways to look at compression.
Yeah, I guess we can end the session here. Thank you so much for your time. It was really
Yeah,
an insightful session.
thank you so much. Have a nice day.
Have a nice day. Take care. Bye.
Bye.